if you think back to our very first reaction this term, we were adding HX we're adding HX to an alkene. So we would, if we had something like this, so HBr, this was the Markovnikov addition in which, let's draw a little mechanism. We would form the most stable carbocation, most stable and then our bromide would come in and attack that, and we would end up with, we added X to the rich got richer, and the bromide would go on the most substituted carbon. Now, for a lot of the other reactions that we've done this term, there's been something interesting which has happened. So if we had a similar sort of similar molecule here, if we were adding water, I'm going to put it in brackets, we had two reactions we could do. One which would give us the OH on the least substituted carbon, and one which would put the OH on the more substituted carbon. So we could do the hydroboration here, THF. Or it could be the, say, the oxymercuration reaction, water and THF, followed by the reduction with sodium borohydride. We just did a reaction with, if you had a double bond, where we could make the cis diol versus do it another way where we could make the trans diol. So chemists have basically developed ways of doing complementary reactions, right? So adding an OH to the more substituted carbon, adding an OH to the least substituted carbon, making a trans diol, making a cis diol. But we haven't seen yet how to make, let's erase this. This is one of the reactions that has been kind of left out of our toolbox as of yet. How to make this. Adding HX across a double bond in which anti-Markovnikov, so the rich don't get richer. The rich get the BR and the poor get the money. So we haven't done this as of yet. So what we're going to do today is talk about how to do this particular type of reaction. And the fun part is that this is going to be some radical chemistry. So remember, in radical chemistry, the bonds are broken are broken / formed homolytically. So we are going to be using fishhook arrows. Okay, now we did see a radical reaction a long time ago. It was basically a substitution reaction, and we're going to see a couple other ones. We're going to actually look at a substitution reaction today and an elimination reaction today. Not elimination, sorry, addition reaction. Okay, so let me think here. What's the best way to start? The best way to start, I suppose, is to look at radical stability. Let's do that. Because this is going to dictate a lot of the chemistry that we've seen so far. So if we look at a methyl radical versus a primary radical versus a secondary radical versus a tertiary radical. What we are going to see is that green, let's do green. So what we're going to see is that tertiary radicals are the most stable, methyl radicals are the least stable. And so if we were sort of doing a, so these are tertiary are more stable than secondary, secondary are more stable than primary, primary are more stable than methyl. And so this trend, what does this trend follow? When we're thinking back to some other trends that are very similar. Right, these things exactly mirror carbocation stability. So it basically mirrors carbocation. And one of the ways that radicals are stabilized is through hyperconjugation. So this makes the more R groups you've got, the more stable they will be. So this is important for when we're doing our that first reaction. There are some other radicals that are quite stable as well. And so let me think of this. Let me do these. So if we were looking at, remember when we were doing our, this carbon here and this carbon here have special names associated with them. Do we remember what they were? We did this way back in Organic 1. So remember there was a couple of resonance. Right, so one of these, this one over here is the allylic carbon. And this one over here is the benzylic. I think I spelled that wrong. So, and when we were talking about an allylic, we saw allylic before in particular because we were using it as for a recognition pattern for resonance structure. So if we had an allylic lone pair, so we could draw a resonance structure that looked like this. Positive, negative. Or if we had a allylic carbocation, we would draw something like this. Those electrons go there, resonance structure. So these are recognition patterns for resonance. Now, similar things can be, both the allylic and benzylic radicals are stabilized by resonance. So we could draw a very similar resonance structure. I'm going to draw out all of the carbons just so everybody can see. So if this is resonance stabilized, we would draw our resonance structure like this. Fishhook arrow goes to make a pi bond. Fishhook arrow goes to make a pi bond. Fishhook arrow goes onto the carbon. And we would have this. And it could go back the way it came by doing something very similar. Like these go there, this goes there, this goes there. And with regard to benzylic radicals, we could draw something very similar. So in this case, we have got a ring, CH2, and we can delocalize this single radical inside this ring. So these electrons go there, these electrons go there, these electrons go there. And we can draw some resonance structures of this. And we will go all the way around the ring with this. Do one more. Let's choose red. And then the last one, we'll use this space one. That looks good. Take us there. So both benzylic and allylic radicals are stabilized by resonance. So both of these are, so we're going to see that we can use allylic radicals, benzylic radicals, and of all of the three at the top, the most stable tertiary radicals. So we're going to see this in a second. So now when we were doing our radical chemistry before, the radical reactions basically had a number of components. They had an initiation component. There was a chain reaction. And there was basically a termination step. And the way you initiate a radical reaction, there's basically two ways you can do it. You can do it with heat, or you can do it with UV light. And UV light's a popular way of doing it because when you're adding heat to the system, you're providing more energy to it, and so you can generate basically some side reactions and that type of thing. And some compounds just aren't stable to heat. So UV light is a nice way of doing it. So whenever chemists, we just put HV there. And there was a couple of, if you wanted to initiate a reaction, there was a couple of initiators that you could use. So the one which is common in the lab is using peroxides. So ROOR. And there's a variety of different things that R could actually be. But the key point is that under UV light, this oxygen-oxygen bond is homolytically broken. So you generate two radicals times 2. So that peroxy bond is particularly weak, and it gets broken. I think in the previous example, which we were doing, the bond that we were breaking was a chlorine-chlorine bond, and that bond isn't particularly strong either. So under UV light, we would generate two chlorine radicals. Okay, so the way that this works is that if you've got your alkene and you've got HBr, you're going to submit this reaction to UV light, but you have peroxides in them. Oops. Let's make this arrow longer. And our final product is going to be the anti-Markovnikov addition of HBr. So the proton or the hydrogen atom is on the more substituted carbon. So H is on the more substituted carbon. So the main thing we're doing is we're adding the peroxide to the reaction. And the second key fact is that we're making this reaction a radical reaction by using UV light. So how does this work? The mechanism. So the mechanism. So the first step is what we've seen before. That under UV light, these bonds break homolytically, and you make RO times 2. So this is going to be the initiation step. So when we're doing this reaction, you just need a tiny amount of your peroxide, and it's going to generate a tiny amount of radicals, and then they're going to do the next part. So the next thing they're going to do is they're going to break basically the weakest bond that we have in the system. And Right, so yes. Yes, this is interesting. Okay, so HBr. One of the interesting things is that, and I think we did this before, the OH bond is a particularly strong bond, but the reason why we're breaking it all the time is because we're doing the reaction under, we're doing all our polar reactions under heterolytic cleavage, where this reaction is taking place under homolytic cleavage. So we are going to break the oxygen, sorry, the hydrogen bromine bond and make an alcohol. Plus we are going to generate a bromine radical. And this bromine radical is going to add to the double bond. So I'm going to do two different ways that this could happen, and we are going to see why it goes where it goes. So we'll use this as our molecule again. So there's two possible ways we could do this. Okay, so one way is that it adds to the least substituted carbon. And there's the other, there's that. The other possibility is that it adds to the least substituted carbon. So we'll hook that around like this. Sorry, the other way is it would add to the more substituted carbon, and that would generate this. Okay, so here are our two potential radicals. The pink one and the green one. So the first thing we're going to think about is which radical is more stable. Because if we've got if we just think of an energy diagram here. So here's our free energy. Here's our reaction coordinates. Here's our starting material. We are going uphill here, right? So we are generating a radical. So are we generating a radical like this, or are we generating a radical whereabouts on this energy diagram is our radical, our intermediate? So we're going to want to form the least substituted, the more stable radical. So based upon the information above, this is a primary radical. And over here, this guy is a tertiary radical. And so tertiary radicals are more stable than primary radicals. So it should be this tertiary radical which is formed preferentially. So this one is the one which is formed. And there's a couple other things so the intermediate's is the least stable. So, I mean, sorry, is the most stable. So that's one reason why this forms, this one will form preferentially. That's the main reason. But you can also think of it as in the sense that the radical is actually attacking the least hindered carbon as well. So that's going to help too. But it's really the radical stability which is the key part here. So so we're going to form the tertiary radical. So in our mechanism here, the next step is going to be, oops, I got a question. Okay, so okay, let's see here. What's the best way to describe this? Okay, so whenever you're doing fishhook arrows, questions about fishhook arrows. So if you're making a bond, the two fishhook arrows should come together. So that's saying, okay, I've got a radical here, I've got a radical here, and let's just call this carbon. Call this, I don't know, X. So when the two little points are coming together, this means that you're making a bond and you would have X. So you've basically formed this bond here. If you're breaking a bond, and this could be a sigma bond, this could be a pi bond. So let's use, because we're doing pi bonds in this example here. So we've got our, okay, and we'll call this carbon. So we've got our Br coming in. So when we're breaking a bond, I'll make this red, I guess. The arrows are basically telling you, the fishhook arrows are telling you where that radical is going. So one carbon, this little carbon in the red box, it is getting the red pointy, the fishhook arrow. The carbon on the other side, which we'll draw in yellow, if we draw this going over to this bromine, and the bromine is making a, so these two arrows are coming together here. So this means that a bond is being formed on this end, but this pi bond is being broken. And that means that the carbon in red is getting that arrow. So our final product is going to look like Br. And now we've got this radical on this, oh, I guess I better make it red. It's red. So that carbon now has that. So the little end of that red point, the fishhook, that's going, it's telling you where that is going. So it's going to that carbon. So in these examples over here, so this pink arrow is saying that this carbon in green is getting that radical. And in this, for the green lines, I'll draw this in yellow because I'm not that organized. This carbon is getting the electron because the green pointy arrow is pointing towards that carbon. And so in each case here, and I'll draw these in blue, the bromine's making a bond there, or the bromine's making a bond there. So that's basically how the little pointy things work. So the two ends want to come together when you're making a bond, and when the bond's being broken, it's going to tell you where it's going. So So yeah, there's a little bit more, you sort of have to pay slightly more attention, I guess, when we're doing these sort of things. Okay, now the next step, right, in our sequence is that we have this radical. And remember, this is a chain process. So you're going to have another molecule of HBr. So you only have a tiny amount of peroxide in your reaction. And so when you, or even if you have more than a tiny amount, when you use your UV light, it's not actually breaking all of those peroxide bonds. It's just breaking some of them. So this radical reactions are chain reactions. So then the next step in the chain is going to be that we make a carbon-hydrogen bond. And we break the hydrogen-bromine bond, and this will generate our final product. Plus, it's going to generate our radical. And then this radical is going to return reaction. Because this is what we started with once the peroxide. So it returns to the chain reaction. So this guy will be coming in and it will be adding to and then this one is basically right there. So this just keeps on going until you run out of materials. So yeah, so that's basically how you do a anti-Markovnikov addition of HBr. You just make sure that you include some peroxides in there and hit it with UV light. So we now know that HBr and this involves a carbocation. So this would be a polar reaction, polar, and HBr, UV light, and ROOR, and this will give us the anti-Markovnikov, and this involves a radical. And it's funny, in both of these cases, the intermediate here is the most stable carbocation, which is on the tertiary carbon. Here, the intermediate is the radical on the tertiary carbon, which is the most stable intermediate. So each one of these, it's basically got the same concept. Our high energy intermediate is the lowest energy of those high energy intermediates. Now, there's radical chemistry is actually, you can do some really interesting things here. And I want to show you just two other reactions that are quite helpful. And the first is what we call a bromination reaction. Radical, I guess I'll put in brackets. So you can take basically an alkane, and you can react it with NBS and UV light, and you can form an alkyl bromide. And specifically, you can form the alkyl bromide on the tertiary carbon, right? So there's, if you think about it, there's a whole bunch of different, how many different possible products could we form here? We could form how many different constitutional isomers are there? I count 4. And the one we make selectively is this one. And so to basically understand how this works, and we need a initiator of some type in this reaction. So let's put in. Okay, so MBS. Do we remember what MBS was? It was this fellow. And at the time, I said it was a source of Br plus in quotation marks, or Br dot or radical in quotation marks. And so during this reaction, what ends up happening is if you've got your starting alkane, so you've got all of these carbon hydrogen bonds, and you've got your source of OR, sorry, that's your initiator radical. You can break, all of these carbon hydrogen bonds aren't equal when it comes to bond strength. So we've got 3 here on this carbon, which that's a primary carbon. And then we've got, so this would be primary. We've got a series on these carbons here, which are all secondary. So we'll draw that secondary. And we've got 1 carbon, which is green, tertiary. So the various carbon hydrogen bond strengths there is basically dependent upon what type of carbon you've got. So for this, for primary carbons, a CH bond is approximately 410 kilojoules per mole. For a secondary carbon, the CH bond is approximately 397 kilojoules per mole. And for a tertiary, last time I looked it up, CH is approximately 381. So it's the weakest bond out of the lot, and so it's the one which is preferentially formed. So it's going to, your radical is going to break that CH and it's going to generate that stable tertiary radical. So if I drew that little hydrogen here, the way this would work is that this would go there and this would go there. And then the radical is going to come along and grab the, it's going to form the carbon-bromine bond, which will make our product. And you'll generate the succinimide radical, and it's going to continue the chain up. Where's a little colored arrow? This guy is going to continue the chain here. Instead of OR, it's now N with the N radical, so the nitrogen-based radical. So that's basically, so there's a couple of select, so if you've got just a straight up alkane, you can selectively brominate on the most substituted carbon. So as long as there's a CH bond, so a tertiary carbon, if you used NBS, a peroxide, and UV light, you are going to make this. In fact, sometimes you don't even need the peroxide because NBS, it's an interesting compound. Over time, NBS converts into you generate a small amount of bromide. And so if you've got a little bit of bromide in there, that can be the initiator. You can end up breaking that bond. And then it'll abstract the proton or the hydrogen and then start the chain reaction. So, but if you use a peroxide, it's going to work for sure. So if you've got something like this, it works 100% of the time. Or if you've got an allylic carbon, oh, I guess we're running out of time here. An allylic or a benzylic, we'll explain this, I guess, little bit later on in the next class. But if you use NBS and UV light, NBS and UV light, you can selectively brominate in those two positions, the benzylic position or the allylic position. So the allylic or the benzylic. So benzylic or the allylic. In this case, it's a symmetrical, in the case of the allylic one here, it's a symmetrical molecule, so it doesn't matter if it's left or right. So those are some other potential things. So the bond strengths of an allylic CH bond, just for your reference, allylic, that is 364, which is lower than the tertiary, and the benzylic CH bond is 356. So it's getting lower and lower and lower. So these are popular, these two in particular, the allylic and the benzylic, these are both popular reactions in organic synthesis. But it's a neat way of introducing bromide. Remember, of course, the bromine is going to be a good leaving group. So this is a really interesting reaction to have in your toolbox. So yeah, the key point for this is that you can do the exact you can take a regular alkane, brominate the most substituted carbon, or do the anti-Markovnikov addition of HBr. Yep, that's what I wanted to get through today, I guess. Are there any questions before we take off? I'm about 5 minutes late or 3 minutes late. Okay, well, if not, have a super fun day for the rest of the day, and I'll see everybody on Thursday.
Thank you.
You bet.